So, since you have an exam on Friday, I figured today's class will be a little bit of semi-light entertainment. You can think of today's class as an extended advertisement for taking the classes in general relativity and cosmology. You finished talking about special relativity, so now you know everything about Lorentz transformations, all their weird, wonderful properties. What I want to do today is give you some sense of how that then can be extended to think about more complicated phenomena that will eventually lead to general relativity. I'm going to begin with a disclaimer. As you can see, there's a cartoon on the screen. And the cartoon is appropriate for two reasons. One is that everything I say will be a hand-waving approximation. And that's simply because the space-time is like a complex set of equations. The complex set of equations don't neatly fit into a 15-minute package. The second is that I'll work as much as possible by analogy and try to draw it in from things that hopefully you already know towards hopefully interesting results. So I'm going to begin where you are with special relativity. And the general principle, the thing that makes special relativity different and interesting and fun, is that the speed of light is the same for every observer. So let's imagine you set off some object, you have some object that emits a pulse of light. If you have an object that emits a pulse of light, after some time t, or delta t, that light will have spread out in all directions and will occupy a sphere whose radius is c squared, c delta t. And since I don't like square roots, I'm going to square both sides. So what's special about special relativity? If everybody agrees that the speed of light is constant, then everyone will agree about this calculation. And in particular, if I now take these numbers on to the other side, this is an equation which everybody will agree on. In any frame, any observer for which the speed of light is true, this will be true. And that means that if you have another observer in another frame whose coordinates are t prime, x prime, y prime, and z prime, this is also true. What's remarkable is that this is not just a property of light. This is a property of coordinate systems. You found something that is invariant under the transformations from one frame to the other. And it's driven by the constancy of the speed of light, but it turns out this is a fundamental invariant. It's the length of something. You're used to thinking, say on the blackboard, the length is some delta x squared plus delta y squared. It gives you the length squared. This is length in space-time. If I divide by c squared, this gives me something whose units are time, and so it also is the time, sometimes called the proper time. It's called the proper time because, of course, if you're at rest, delta x, delta y, and delta z are 0, and so delta, this constant here, call it delta tau squared, is the time that an observer at rest measures. Having invariant quantities is a terribly useful thing because it is one of those things that generalizes from the study of special relativity to the study of general relativity. The other thing that makes special relativity special is its focus on inertial frames. And you've hopefully seen and come to appreciate how Lorentz transformations are part of a set of transformations that link an infinite number of these frames together. As many inertial frames as you want, all specified by a different velocity, and therefore a different velocity vector, all specified by different rotation or change of coordinates by just adding a constant translation. If these set of frames are essential to all the calculations you did, and since there are infinitely many of them, you might think that this is enough to do anything you want. The problem is that inertial frames are by definition the frames in which Newton's first law works. And that's the great flaw in special relativity. Because it turns out to be incredibly hard to figure out if you're an inertial frame at all. So we usually say, oh, this room is an inertial frame. The room is clearly not an inertial frame, because if I release this thing at rest, it does not stay at rest. There's something pulling down, call it gravity. And since there exists no gravity shield, right, if you want to take eliminate electric fields, you can build yourself a Faraday cage. It's a little bit harder to build yourself a magnetic box, but there are techniques for reducing magnetic fields. No one has invented the gravity box to get rid of it. And that means that anywhere near the surface of the Earth, you are not an inertial frame. You have this unescapable force. And you might think, well, let's go off, I'll leave the orbit of the Earth and go, say, in the space between the Earth and the Moon. In fact, gravity, because it's an infinite range force, never leaves you. And it's worse than that, because even if you can somehow arrange so that you are equidistant or at the center of mass of any distribution of objects you know, there is almost infinite. There are billions and billions of stars and galaxies in the universe, and each of them exerts a small gravitational effect on you. Tiny, but enough to make you not an inertial frame. And in fact, we do not know of any way to define where you are in an inertial frame. If you think about it a second, this is really bad, because it means that everything you learned in the last, was it 3 weeks, 4 weeks, is meaningless. Almost. So this troubled Einstein. Einstein came up with a special theory of relativity in 1905, and he worried about this for years. And he worried about it for years, not because the physics of figuring out what was wrong was hard. He came up with what I'll get to as the equivalence principle relatively quickly. He worried about it for a long time because the math is actually much, much harder than the physics. Einstein was thinking about how to deal with this effect of gravity. Why gravity? Because gravity is the thing you can't shield. So determining whether you're in an inertial frame is ultimately down to figuring out how can I account for the effects of gravity. And what Einstein realized is that you can set up an equivalence in gravity if you just consider a local measurement. So the standard thought experiment that's made is you put someone in an elevator. Hopefully not the ones in Barris and Hawley. Highly non-inertial. So you put someone in an elevator and you ask them to do an experiment. Drop a ball, or in this case, a piece of foam. And they drop the foam and the foam falls to the floor. And you ask them, okay, what's causing the motion of the phone? What Einstein realized is that there was a fundamental equivalence as long as you could not make any measurements of the outside world, so no windows to your elevator, between whether the elevator is sitting on the surface of the Earth and pulled down by the force of gravity, or the elevator is sitting in some fictitious empty space far enough from anything else and being accelerated up at an acceleration equal to gravity. And to understand this, sorry, my ability to draw stick figures is very limited. To understand this, let's think about this situation. This is our fictitious inertial frame, is the frame in which this piece of foam is floating, has just been released. There are no external forces. It's floating. There's no air resistance. Well, imagine it's some sort of vacuum that a person can breathe in. If this is truly an inertial frame, then the foam will float in the air. But unfortunately, the elevator is moving. And so the person will not see the foam float in the air because they'll be moving up relative to the foam and accelerating up. So the physical description from the outside world of these two pictures is very different. In one, you say, oh, the foam fell down because of gravity, but I'm not moving. In the other one, an external observer would say, oh, yes, the foam is standing still, but the elevator is accelerating up to meet the foam. But the key that Einstein realized was that if you're inside an elevator and can't tell the difference, then you really don't know which of these two things is true. Let that sink in for a second. There are some caveats. If you did this experiment on the surface of the Earth with really accurate measurements, you would realize that the force of gravity pulls towards the center of the Earth, and if you drop something from this side of the elevator and something from this side of the elevator, they would actually fall in slightly different directions. But that's just a function of the size of the elevator. If you make your elevator smaller, the directions become smaller as well. So you have to imagine a really small elevator where you don't see any difference. Similarly, you need the elevator to be small enough so that the acceleration due to gravity here is the same as the acceleration due to gravity there. Well, gravity is a distance-dependent force, so the accelerations are slightly different. But again, if you make a purely local measurement, this is equivalent to this. The apparent trajectory of the foam will be the same. Everyone prepared to buy that? Good. You have to buy this by the next step. It is actually true. This is not what's important. What's important is that once you've made this equivalence, this can actually be turned. There's an example of this, which is a truly inertial frame. If we now set the acceleration of the elevator in space to 0, Einstein's dead. What is this equivalent to? Anyone want to hazard a guess? Yeah. Instead of being at rest, it's equivalent to turning all the accelerations down. So this is now equivalent to something that is accelerating down at g in a gravitational field g. And that's free. And this is magic. It's magic because this is an inertia. And therefore, this is an inertia. And all the wonderful things that come with special relativity now suddenly become possible again. long as you're freely falling in a gravitational. So what Einstein discovered through this, which is called the equivalence principle, for the true aficionados, this is the weak equivalence principle. What Einstein discovered is a way to get around this fundamental problem of knowing whether you're in an inertial frame. The fundamental problem is caused by gravity. You don't know how to account for the effects of gravity. Well, now you do. You let something fall. And the freely falling frame under gravity is the frame which is inertial. I have two quick demonstrations of this. They're both variants of the same thing. They're sometimes referred to as the old man's toys, because apparently they were given to Einstein as a birthday party present sometime in the 40s. This one, and the other one was actually developed by a late professor here. The basic idea of this setup is that this is a childhood game, the hoop and cup game, where you have a little hoop and a cup, and you have to try to get the hoop and the cup. And I've had a bit of practice, so I can actually get this to work some of the time. But it's generally hard. The only thing that differs in this game from the childhood game is that we've connected a very weak spring to this string. The spring is so weak that if I'm holding the stick, the presence of the spring doesn't really help me very much. But if I were to somehow eliminate the effect of gravity, then the only force on the ball would be the spring force, which would pull the ball in and make it fall into the cup. And if I want to eliminate the effect of gravity, all I have to do is to move to the inertial frame and drop the stick. And it works every time, as long as you don't tilt it. If you hold the stick tilted at the same time. A variant of this, developed by Hendrik Gerritsen, is to use a weak magnet. Again, the magnet is so weak that in the presence of gravity, the force of gravity completely overwhelms it. But in the inertial frame, the gravity doesn't exist, and the magnetic force is the only thing present. And the two magnets come together. So hopefully I've convinced you of this wonderful thing about the equivalence principle that tells you how to get into an inertial frame in the presence of gravity. You move this freely. And because you can then calculate anything in the freely falling frame, you can calculate all the things that you need to do about special relativity in this frame. And if you need to calculate at some other position, well, then it becomes hard. The reason it took Einstein 10 years to move from special relativity to general relativity is not the equivalence principle. It's the problem that this only works in a small region of space. The hard part of relativity is stitching together what are called these locally inertial frames. So if you have a little elevator here, you can move to the inertial frame here, but that inertial frame is not the same as the inertial frame here. And in general, knowing what to do about extended distances involves differential geometry. This is not a class that's going to deal with differential geometry. I'm going to leave it at that. But I do want to highlight the fact that the problem is not a physical problem. It's not that conceptually there's anything hard about understanding the residue. If you want to understand any physical phenomena in the presence of gravity, you do the calculation in locally inertial framing. At every point along whatever trajectory the particle has. mass. And the problem is that you have to transform between the locally inertial frames all the way along the trajectory. And so the math becomes hard, but the physics is not. I should also point out that there's a stronger form of the equivalence principle called the Einstein equivalence principle. The weak equivalence principle tells you that you cannot distinguish between the acceleration due to gravity and the acceleration due to anything else. So it is a statement about dynamics, about the motion of particles. Another way to think of it is the weak equivalence principle tells you that the two things you've written down as m without thinking about it for all of your physics career really are the same thing. Right? You've written down Newton's first law, F equals ma, where there's some m which tells you how much inertia something has, how much force is required to accelerate it. And you've written down the gravitational force exerted by an object on another, where m is the amount of stuff, the mass that causes the acceleration. And in many, many cases, for example, when you solve the Kepler problem, you did it last semester, you of course said, well, the m's cancel. But that's a postulate. Right? Those are just constants. Newton said, well, let's put the same constant, and it turns out the math works. The weak equivalence principle requires those two things to be the same. The inertial mass and the gravity. It turns out the weak equivalence principle isn't quite enough to give you general relativity. To give you general relativity, you need something else, which is to imply that not just dynamics is the same in the two situations, but all the physical experiments in the two elevators are equivalent. What does that mean? Well, suppose that dropping the ball in the presence of acceleration changed its spin. Then the trajectories of the particles would be the same. But you'd be able to tell whether you were in a gravitational field or whether you were in an elevator being accelerated up. That would not violate the weak equivalence principle, but it would allow you to tell which situation you're in. As long as you have the Einstein equivalence principle, your local experiment cannot distinguish between these situations. And that's important because it allows you to think of the effect of gravity as being something that changes the motion of everything in an indistinguishable way. And this is the key to what's called the geometrical moment, in which you think of the effect of gravity as a curvature of space. The curvature of space affects everything, and therefore every property is affected equally by the difference. If you did not have the Einstein equivalence principle, you could not think of gravity as being due to the curvature of space. Okay. Are there any questions? The equivalence principle has many measurable and testable consequences. Let's think about just one of them. Let's think about gravitational redshift. For this experiment, the thought experiment, I'm going to imagine that I'm sitting at the floor, shining a beam of light up at the ceiling. So I have a beam of light going from floor to ceiling. I have an elevator whose height is h. And at t equals 0, I should turn on the light. The speed of light is always c. And so the light reaches the top at t h over c. That's going to be true always. Now let's use the equivalence principle. Let's imagine you are in that elevator that's accelerating up at g. When the light reaches the ceiling of the elevator is moving. Even if you started at rest, because it hasn't picked up a velocity, which is 1/2, oh sorry, distance. 8. Right, one step ahead. So if I'm approximating the effect of gravity, this is gh over c. It's moving up at that velocity. Now, of course, the observer at the top of the elevator, at the ceiling, has to see the light moving at the speed of light, because the speed of light is always constant. But it detects a Doppler shift, because now it is moving relative to the light source at a velocity equal to gh over c. And so the Doppler shift that's measured remind you, the Doppler shift is the change in wavelength divided by the wavelength. And that's v over c. And that's gh over c squared. In other words, the wavelength that is measured is the wavelength that's emitted times 1 plus gh. Everyone agrees with this? So this is a calculation done in empty space in an accelerating elevator. But the equivalence principle says that's the equivalent situation to an elevator at rest on Earth. And that means that if you sit here on Earth and shine a light from the bottom of this room to the top of the room, the light will be detected at the top of the room redshifted by a factor of 1 plus gh over c squared. You've just discovered that they're in the presence of a gravitational field. Light has to redshift. The equivalence principle forces you into that. You can redo this experiment if you're willing to change the idea that the gravitational g, the gravitational acceleration, is gm over r squared. So you can think of this as being due to the mass of the Earth times your distance from the Earth and the change in your distance from the Earth. It's a change in the gravitational potential. how big is this effect? Well, let's calculate it for this room. This room is 10 meters high, something like that, a little bit less than 10 meters is a nice round number. It makes the calculations easier. So delta lambda is gh over c squared. This is 10 meters per second squared times 10 meters. And unfortunately, c is a big number, right? C is 3 times 10 to the 8 meters per second squared. So this is 100 divided by 9 times 10 to the 16, which is 10 to the minus 2. Which is very small. Amazingly enough, this measurement has been made. This is the basis of the extremely famous Pound Revcap experiment. I have to remember how to spell Revcap. It's a B, right? B. Never remember if it's a B or a P. It's an experiment done in 1960 in which 2 identical iron crystals were placed separated by a height, I believe it's 15 meters. Well, separated by some height h. And the idea is that each crystal emits, it can emit and absorb a very, very small, a very, very tightly, very monochromatic wavelength of gamma rays. This is a collective effect which I'm not going to try to explain since someone who knows much more about it is in the room. But the key is you emit gamma rays at 14, it's 14.4 kV. And because the energy of the emitted photon is so tightly constrained, the energy of the absorbed photon has to be the same. And so what they did was they put a detector behind the crystal and said, would the photons be absorbed by the crystal? Because the energy range is so small and the crystals were identical, if the detector was held constant, there would be no absorption because of this small shift in the energy. In fact, they could demonstrate this. What they did was they put this thing on a spring. By moving the upward detector, what they found was that at certain points, the velocity, the Doppler shift, due to the velocity of the detector, exactly matched the gravitational redshifting, and you got absorption. And you got absorption exactly when the Doppler shift matched this gravitational Doppler. So this has been confirmed. Gravitational redshifting is actually real. It's since been observed in a whole bunch of astrophysical phenomena. But it's always nice to do things in the lab. I want to give you an equivalent way of thinking about gravitational redshifting. If you remember, in special relativity, moving clocks run slow. And so if you imagine each crest of the wave and the frequency of the crest of the wave, the time frame is just, between the crests of the wave, is just 1 over the frequency of the light. The Doppler shift tells you that this is equal to delta t0, 1 minus, sorry. If the Doppler shift in frequency is this, the Doppler shift in certain wavelength is this, the Doppler shift in frequency is 1 minus this. And that means that the time at the bottom of the elevator is related to the time at the top of the elevator by 1 minus g. So clocks on the surface of the Earth actually run slower than clocks in airplanes. Again, this is a classic experiment that's been done. Actually put atomic clocks on airplanes and flew them around the world. They had to fly them around the world both ways because they're a non-inertial effect. The direction in which you travel. And verified that the clocks in the airplane run a few nanoseconds after the end of the trip around the world. We're a few nanoseconds faster than the clocks in the base. Okay. One last thing about moving elevators. You can use this equivalence of the moving elevators to prove an effect that's near and dear to my heart. Just gravitational waves. Let's now imagine we have a light beam shining from one side of the elevator to the other side of the elevator. If the elevator is at rest in empty space, the light beam is going to go straight across. Imagine what would happen if the elevator were actually moving. If the elevator is moving in a constant velocity, of course, by the time the light has reached here, the elevator has moved a distance v times t. So now I need to know width. So the time, the distance is just w over c. So if the beam were moving at constant, if the elevator were moving at constant velocity, you would still see a straight line, but it wouldn't hit the wall at the same time. But what happens if the elevator is accelerating? If the elevator is accelerating, when the beam hits the far wall, the distance the elevator has traveled is 1/2 a times t squared, which is 1/2 g, and t is w over c, so this is w squared over c squared. What you see is that the light has bent by that. So if I were to draw this, it's in the next. In the presence of acceleration, the light is bent. Again, that accelerating elevator is equivalent to something at rest in gravitational field. So if I shine the light across the room, the light gets bent. By how much? By a tiny amount. Right? The effect still has a 1 over c squared. Anything that's g over c squared, well, we calculate it. Right? The distance, again, about 10 meters across. is 100 times 10 divided by 2 times 9 to the 16th. So that's 1/20th times 10 to the minus 13th, which is 5 times 10 to the minus 15. That's a hard measurement to make. But of course there are stronger gravitational fields that act over much longer distances. So if you have a much larger path length, you can get a much larger. This actually leads to an interesting way to a geometrical conception of gravity. Because if the path of a light ray in the presence of a gravitational field is curved, so is the path of everything else in a gravitational field. We're used to, when we think of our mechanics from first year physics or high school physics, to think of things as moving in straight lines if there's no force acting. In fact, that's Newton's first law. So you can revise Newton's first law in a gravitational field. I'm going to mix my notation horribly, so again, if you think of it, the path that light takes, that's equivalent to the straight line. You're just moving in a frame where the trajectories of everything are curved. The paths of things are called geodesics. These are the equivalent of the straight lines. And if you think of gravity, as general relativity encourages you to do in terms of the curvature of space-time, then gravity doesn't exist other than curving the space-time. Newton's first law holds perfectly well. If you, in the presence of anything other than gravity, things will move in a straight line. Well, your straight line is now a geodesic. What is a geodesic? Well, a geodesic in a curved space is the equivalent of the straight line. It's the curve of extremal separation between any two points. So on the surface of the Earth, or on a globe, if you want to get from point A to point B, the shortest distance between point A and point B is the great circle connecting. So it's the circle that goes through the center and connects point A and point B. That's why when you fly from here to Europe, you look at it in a Mercator projector map, you'd say, why would you ever want to go past Greenland? The reason you go past Greenland is, of course, that the geodesic that connects us and London, or us at home, so I have more practical experience doing that, is one where the great circle doesn't go straight across. That's a circle that doesn't cross the center of the Earth. That's not a great circle. So the separation on a curved surface, the curve that connects the 2 points on a curved surface is the shortest distance between the 2 points. There's a little bit of a complication. I don't know if you talked about this, but in space-time, so if you write an xt diagram, and you have points A and point B, and calculate the separation between them, at first you think, oh, separation, that's a horrible thing, right? Length contraction means that's not a relativistically invariant thing. It depends on your frame. But it turns out there is a separation that you can define. It's the length in space-time. When you do that, you will discover that the length in space-time is longest on this line connecting the 2 points. So you have to amend your thing to call this the extremal distance between 2 points. can be both a minimum, either a minimum or a maximum distance. Incidentally, this is why the twin paradox isn't a paradox. Right? In space-time, in space, you do not have any problems thinking that two different trajectories that come back to the same point have the same distance. So why should it be any different in space-time? The two twins go and come back, and they leave at the same point in space-time, and they come back and they're both at the same point in space-time. And they're just taking two different trajectories through space-time. It turns out that the longest trajectory through space-time is the straight line. And so the twin that goes straight up along the time axis has the longest time. There's nothing more to it. Okay. In relativity, you can express the distance formula in terms of this quantity delta tau squared as just being some quantity times the coordinates. Introduce this notation, where this thing is called the metric tensor. It's called the metric tensor because it allows you to describe the position of objects, to calculate a distance from any coordinates. The metric tensor is not coordinate independent. You change your coordinates, the metric tensor changes, but it changes in such a way that if you change your coordinates, this quantity doesn't change. So for the space of special relativity, you can read it off from that expression there. This thing has 16 components, one for every, since there are 4 dimensions of space-time. And it's nicely represented as a matrix. The matrix has dimensions minus c squared, or in this dimension it's c squared, minus 1 and minus 1. And then everything else is 0. There are no delta x, delta t terms. The effect of a gravitational field is just to change your definition of the distances. By curving space, gravity alters the metric. And the metric encodes then all of the effects of gravity. And so in general relativity, for example, near a massive object, you would rewrite the metric near a point mass. It would look like zeros. It's easiest to work in spherical polar coordinates, right? Because there's a spherical symmetry around the point mass. So these are the coordinates will be t, r, theta, and phi. This is minus 1 over 1 minus 2gm c squared r. In polar coordinates, the theta term has a minus r squared in front of it. Squared r. If you take this to be your definition of distance and calculate Newton's first law, just the shortest distance between the two curves, this allows you to calculate the trajectories of any. So the planets going around the sun are traveling in what they think are straight lines in a space defined by this geometry. That is what the theory of relativity does. The math, of course, is painful once you add those things in, but the physics is not that much So hopefully, this has given you enough of a teaser to think about how you can extend special relativity to account for gravity. As I said, there's an entire course devoted to it. One 50-minute class doesn't